Yeah, greetings from K.S.Rangasamy College of Technology, Tiruchengodu. Myself, U. Vivek, Assistant Professor, Department of Mechanical Engineering, K.S.Rangasamy College of Technology. Today, I have taken the subject Composite Materials under the module Design. So, where is failure prediction in the composite material? We have to one by one will be discussed. First one is the maximum stress theory, maximum strain theory. Failure prediction means the design analysis of a structure or a component is preferred by comparing the stresses or strain due to applied loads with the allowable strength of the material. In case of biaxial or multi-axial stress field, a suitable failure theory is for this comparison. So these types of failure will be come from the composite material, from the lamina and laminate side, from the bonding of the fiber and resin side. So either the maximum shear stress theory or distortional energy theory is commonly used for designing the against the yielding. The fiber reinforced polymers are not isotropic or nor do they exhibit the cross yielding point. So this is the failure theory is developed for the metal or other isotropic material are not applicable to the composite material. First one is maximum stress theory. When the material is suitable for a variety of complex stresses will be in the component side, it is because of challenging to determine the point of yielding or fracture of the material. The various theory of failure have been developed to define the criteria for the failure of the material. So one such the theory of failure is maximum shear stress of the failure. So see the image when the maximum shear strength is actual case of exceed from the maximum allowable shear stress is simple tension on the material case. Example, we can calculate the stress in this side is P equal to uh, sigma equal to P by A, load by area for we calculate from the stress formula. So in the component, the stresses will be from the two stresses will be there. This is on the y-axis for the sigma y, and the x-axis from the sigma 1 or sigma x. So this is the stress will be acting from the component of the composite material. In a unaxial tensile strength of the principal stress at the yield point is sigma 1 equal to sigma y, sigma 2 equal to 0 on the side. So sigma 3 equal to sigma 0. Sigma y means it is the yield stress of the component. The maximum strain theory, next one is maximum strain theory. According to the maximum strain theory is failure occur when any strain in the principal material direction is equal or greater than the corresponding to the ultimate strain. This is to avoid the failure of the strain. So this theory will be briefly explained in the acetacy heel theory. The following heels is using in the anisotropic of the criteria of the metals. The proposal that the failure occurs on orthographic lamina. This is the formula we are using in the acetacy heel. The sigma 11 divided by S2 up to LT minus of sigma 11 and sigma 22 divided by S2 squared and LT. So plus we can additionally adding the another component, another area of the stress is sigma 2 squared of 22 divided by S2 squared of T plus tau of the 1 2. So tau means is the shear stress on this side equal to 1. So this is the acetacy heel theory in the of the lamina sheet. Major steps involved in the ultimate failure of the prediction. First one is the calculate the stresses and the strain in each lamina using the lamination theory. Apply and the appropriate failure theory of the predict with the lamina failed first. So assign the reduce the stiffness and the strength up to the failed in lamina of the composites. And finally, we can recalculate the stresses and the strain in each remaining lamina using lamination theory. So these are the major failure or the ultimate failure of the prediction of the composites. Next one is the design allowable. So we have to design, we can calculate the something, and we have to consider the some following things. We have to discuss one by one. First of all, we can the lamination theory is along with the ply level of the material property of the database. Considering the wide variety of lamination is possibility with the given fiber resin combination. The second method of preferred by any designer signs of as flexibility, creating the new design allowable without the recourse to extensive testing. So here you are we are using in the composite resin for using for the epoxy or polyester and the polypropylene type of epoxy we are using. That side we got to calculating the we got to ply level of the fibers. So for example, this is the charts for the 0 or plus or minus 45 degree or 90 is for mostly using in the carbon fiber epoxy side. So this is the chart will be briefly tell about the for the design allowable in the x-axis from the percentage of percent in the 45 degree of applies and the y-axis is the tensile allowable strength in the y-axis. So this is the graph will be particularly will be come from the move from the step by step process, right? So this is for the design allowable factors to be considering in the site. Next, these are the major design guidelines. The principal steps is designing a composite lamina for the following things we can design. So first of all, the joint design. So joint design is a major one from the designs area. The joint is are often the weakest areas of the composite structure. And the second is the composite material do not be possible for giving the characteristics of by ductile metals, namely they are the capacity of the restitute local high stresses of the yielding. So these are the composite lamina. Majorly we are do from the three type of joining. First one is a bonded joint, mechanical joint created by the fastening and the subtract with the bolt or rivet of the bonded joint and use the adhesive interlayer between the substrats in the joint side. The mechanical joint. First, we are discuss the mechanical joint. So this is the permit quick and repeated disassembly for repairing or replacement without destroying the substrate. So this type of joint we are using the nut and bolt for the using the mechanical joint to require the little or no surface preparation. So this is easily we can handling and dismantle also very easily for the mechanical joint compared with the bonded joint. And the third one is the are easy to inspect the joint quick quality. And fourth one is the recur machining of the hole that interpret the fiber continuity and may reduce the strength of the substrate laminates. And create a high localized stresses concentration around the joints may to introduce the failures of the substrate. So these are the major points we're using in the mechanical joint. Next I come from the bonded joint. So this is the some load over to larger area than the mechanical joint to require the no holes. Compared with the mechanical joint we are using the holes. Here that is not using the holes but may need the surface preparation is mandatory. So reason is for the surface preparation we can do bonding is the most important in the bonded joint. So cleaning and pre-treatment is mandatory for the bonded joint and add very little weight to the structure compared with the mechanical joint are difficult to disassemble without either destroying or damaging. The reason is we can do using the adhesive, so we can do dismantle is very difficult one. So may be affected by service of temperature, humidity and other environmental conditions are difficult to inspect the joint quality. You see the images for the first one is for the shear outside and the second one is the net tension of the failure and cleavaging and a bearing failure combination of these failure mode is possible. This is a basic bonded joint of the variation. Is A is notation as a single lap joint. This is for the double lap joint. We can do both side or we can do bonded. And third one is this single lap with the double strap joint. And the fourth one is a stepped job joint from the step by step one. And finally we can for the stepped joint and scrap joint for the this one. So this is for the basic view of for the bonded joints. Next, I come to the design of tension member. The tension means the pulling load will be acting on the outside of the material. The load will be come from the out direction. This is for the load from the out direction. Here also load from the out direction. This is totally pulling load pull from the these two laminate. So this is for the design of the tension member. So after we can see that it is a poor one, this one is a good one, laminate design. So reason is the bonded joint will be easily you can bonding from this area. Next is design of compression member. So here is the pushing load will be acting on the bond side. So this is for the length. The L it is notation of the length of the compression member. E is denoted as the modulus of elasticity or Young's modulus, and G is for the shear modulus. So this is for the design of compression member. Thanks for watching this video. Keep learning and growing. Thank you.